5.3. The definite integral. The outline of this video is as follows. We will discuss the formal definition of the definite integral and how it evolves from the concept of Riemann sums. We will begin by introducing the notation used for integration and the specific conditions that determine whether a function is integrable. Next, we will cover the fundamental rules and algebraic properties that govern definite integrals, along with their geometric interpretations. From there, we will explore the relationship between the integral and the area under a curve, including the concept of net-signed area for functions that dip below the axis. Finally, we will define the average value of a continuous function and demonstrate how to calculate it using a geometric example. Let us start by translating the notation of Riemann sums into the language of integrals. The limit of a Riemann sum is a transition from a finite approximation to an infinite, continuous accumulation. As we let the number of subintervals go to infinity, the Greek letter sigma, representing a discrete sum, is replaced by the integral symbol, which is an elongated s. Simultaneously, the discrete function values become a continuous function f of x, and the finite width delta x becomes the differential dx. This notation, introduced by Leibniz, elegantly captures the process of summing infinitesimal products of height and width across the interval from a to b. The key takeaway is that the integral symbol represents the limit of a sum as the partition widths shrink to zero. We can now state the precise definition of the definite integral for a function defined on a closed interval. The definite integral, denoted by j, is the specific number that the Riemann sums approach as the norm of the partition approaches zero. For this limit to be valid, the result must be consistent, regardless of how we partition the interval or which points we choose within those subintervals. Mathematicians define this rigorously using epsilon and delta to ensure the sum is arbitrarily close to the limit j when the subintervals are sufficiently small. When this condition is met, we say the function f is integrable over the intervals. In short, the definite integral is the unique limiting value of the Riemann sums. It is important to understand that not every mathematical function can be integrated. Ideally, we want functions that are well behaved enough to have a calculable area under them. Theorem 1 states that if a function is continuous over a closed interval, or has only a finite number of jump discontinuities, it is guaranteed to be integrable. However, functions that oscillate wildly, such as a function that equals 1 for rational numbers and 0 for irrational numbers, fail this test. For such erratic functions, the upper and lower sums converge to different values, meaning the limit does not exist. Remember, continuity is a sufficient condition to ensure that a definite integral exists. We will now establish some basic algebraic rules that make working with integrals easier. These properties allow us to manipulate the limits of integration and constant factors without recalculating Riemann sums. First, if we reverse the order of integration limits from b to a instead of a to b, the value of the integral simply changes its sign. Second, if the upper and lower limits are identical, the width of the interval is 0, and thus the integral is 0. Third, a constant factor inside the integral can be pulled outside, just as you would factor a constant out of a summation. These rules simplify complex expressions by allowing us to rearrange terms and limits. Continuing with our list of properties, we have rules for sums, additivity, and boundings. The integral of a sum is simply the sum of the integrals, meaning we can integrate terms separately. The additivity rule tells us that if we break an interval into two parts, the integral over the entire span is the sum of the integrals over the adjacent subintervals. Furthermore, the Max-Min inequality provides a way to estimate the value of an integral by bounding it between the minimum and maximum values of the function multiplied by the interval width. Lastly, if one function is always greater than another, its integral will also be larger. These properties are essential tools for breaking down and estimating integrals. This slide provides the geometric intuition behind the algebraic rules we just listed. For instance, the additivity rule can be visualized as splitting a large area into two smaller adjacent regions. The total area is clearly the sum of the two parts. Similarly, the domination rule makes geometric sense, because a curve that sits higher on the graph will naturally have a larger area beneath it. The max-min inequality essentially states that the true area under a curve is trapped between the area of a rectangle formed by the lowest point and a rectangle formed by the highest point. Visualizing these rules as areas helps confirm their validity beyond just algebraic proofs. The geometric perspective reinforces that integrals behave like areas of regions. Let us apply these rules to a concrete numerical example involving two functions, f and h. We are given specific values for the integrals of f and h over certain intervals, and we must use our rules to find new values. To find the integral of f from 4 to 1, we use the order rule to reverse the limits and flip the sign of the known value, resulting in positive 2. For the second part, we use linearity to multiply the integral of f by 2 and h by 3, then add the results to get 31. Finally, we use additivity to combine the integral from -1 to 1 with the integral from 1 to 4. By systematically applying the rules, we can evaluate complex combinations of integrals. We now define the area under a graph using the definite integrals. If a function f of x is non-negative throughout a closed interval, the area of the region between the curve and the x-axis is exactly the definite integral from a to b. This definition bridges the gap between abstract limit calculations and tangible geometries. For example, consider the straight line function y equals x, starting from the origin out to a point b. Using our limit calculation, the integral yields b squared over 2, which perfectly matches the geometric formula for the area of a triangle with base and height b. This confirms that the definite integral provides a rigorous way to calculate areas for curved boundaries. Using Riemann sums, we can derive general formulas for the integrals of some basic functions. These formulas allow us to evaluate integrals quickly without setting up the limit definition every time. For the identity function x, the integral from a to b is b squared over 2 minus a squared over 2. For a constant function a(e), the integral is simply the constant times the width of the interval, which represents the area of a rectangle. For the square function x squared, the result is b cubed over 3 minus a cubed over 3. These basic results act as building blocks for integrating more complex polynomial functions. This slide presents figure 5.13. which illustrates how we interpret integrals for functions that are not strictly positives. When a function takes on negative values, the definite integral calculates the net signed area rather than the total geometric area. Regions where the graph lies below the x-axis contribute negative values to the total integrals. For instance, if a curve has equal parts above and below the axis, the positive and negative areas cancel each other out, resulting in an integral of 0. It is crucial to distinguish between the geometric area, which is always positive, and the definite integral, which accounts for sign. The integral represents the area above the axis minus the area below the axis. We can extend the concept of an arithmetic mean to continuous functions using the definite integrals. Just as the average of a finite set of numbers is their sum divided by the count, the average value of a function is the integral divided by the interval length. We define the average value of f over the interval from a to b as 1 over the quantity b minus a multiplied by the integral of f. This formula essentially smooths out the varying height of the function into a single constant level that would yield the same total area. Conceptually, if you melted the area under the curve into a rectangle of the same width, this average value would be its height. This gives us a precise way to discuss the central tendency of a continuously changing quantity. Let us look at an example of calculating the average value for the function representing the upper semicircle of radius 2. The interval is from -2 to 2, so the total width of our interval is 4. Instead of using complex integration limits, we can simply use geometry to find the area of the semicircle, which is 1/2 pi r squared. Substituting radius 2, the area becomes 2 pi. To find the average value, we divide this area of 2 pi by the interval width of 4, giving us a result of pi over 2. This example shows how combining geometric insight with the average value definition simplifies the problem. To summarize, we have established the definite integral as the limit of Riemann sums as the partition size goes to 0. We learned that continuous functions are guaranteed to be integrable, and that integrals follow standard algebraic rules like linearity and additivity. Geometrically, the integral represents the net signed area between the graph and the x-axis, treating regions below the axis as negative. Finally, we used the integral to define the average value of a function, dividing the total accumulated area by the length of the intervals. These concepts form the foundation for applying calculus to accumulation problems. Before we conclude, consider these review questions to test your understanding of the material. First, ask yourself how the definition of the definite integral handles regions where the function drops below the x-axis. Second, reflect on why continuity is a sufficient condition for a function to be integrable, but strictly speaking, not a necessary one. Understanding these nuances will help you apply definite integrals to more advanced problems in physics and engineering.